Welcome back to this channel, and in this video I want to quickly show the proof or this particular expression. Suppose you ask to prove this and probably you just annoying the lecturer, and let's see how we are going to get it done. First thing you want to do, know that, let's take for example, let's say f of t is 3t plus 2t minus 5, and you want to take the first derivative of this particular function. You know it's going to be 6t plus 2, right? Take the second derivative. Obviously you know it's going to be 6. Take the third derivative, you know that's going to be 0. Then have this in mind that the function is y. First derivative means y prime, second derivative means y prime prime, and third derivative still means y prime prime, right? Have that in mind. So now gathering all of these functions together, the function and its derivative, let's take the Laplace of all of these functions. If I should take the Laplace of them, I would have something like this. Now how do I get to arrive at this point? Remember that the Laplace of t raised to the power n is n factorial over x raised to power n plus 1. As a matter of fact, you can use any other functions to express this proof. I just decide to use this particular polynomial. So if I should take 2 factorial over x raised to power t and all of that, I would have 2 factorial to be 2 times 3, that's 6 over x raised to power of 3 plus 1 factorial is 1 times 2, that's 2 over s squared minus 5 over s. Then, as you can see, now note that these represent the Laplace of y, the Laplace of y prime, the Laplace of y prime prime, the Laplace of y prime prime prime. Now, consider the Laplace of y, which is s over 6 over x cubed plus 2 over s squared minus 5 over s. And consider the Laplace of y prime. Okay? If you notice, I can rewrite the Laplace of y prime like this. If you're wondering if this is actually correct, you see that if I should multiply this by s, I'll be having 6 over s squared plus 2 over s minus 5, right? And if I should subtract this function to be 0, I'll be having minus 5 minus 0 plus 5. And obviously 5 cancels 5. Then I have my Laplace of y prime, which means that I can successfully write this as the Laplace of y prime to be s Laplace of y minus y 0, meaning that s multiplied by the Laplace of y, which we just did, will give us this particular expression. Consequently, if I want to consider the Laplace of y prime prime, which is s over 6 over x, I can also rewrite it in this form, that s squared multiplied by the Laplace of y minus s to the 0 of y and the prime. If I should do the rough calculations in red, I would have 6 over x plus 2 minus 5x minus 0, 0 plus 5x minus 0 minus 2. And obviously 5x will cancel 5x, 2 will cancel 2, and I'll be left with 6 over x, which means that this expression is equivalent to the Laplace of y prime, y prime prime. Then I can write it as the Laplace of y prime prime is equal to s squared, the Laplace of y minus s y0 minus y prime 0. Then we can actually conclude that the Laplace of y to the third derivative will actually be in this expression. Okay, so now let's look at the relationship between all of these derivatives. It means that if I should take my derivative to nth derivative, it will be in this format. Notice that if I should have the Laplace of y prime, that is the first derivative, s as the power of 1, second derivative, s as the power of 2, third derivative, s as the power of 3. So if I should go to the nth derivative, s will have the power of n. Notice that as the expression is going from one point to the other, the power of s is reducing by 1. So you see the Laplace of y prime, you say s and there is no more s. Y prime prime s squared, then s, then there's no more s. Okay, so s cubed, s2, s1, s raised to power 0. So we can write s to be in a decreasing power of n. That's why we have n minus 1, n minus 2, and so on. And you also may notice that we have our y prime, our y to be increasing, the derivative of our y to be increasing from no derivative to the first derivative and to the second derivative. That is why we have all of this here. So if I should want to go further, Of course, you know I can rewrite y raised to power n to be the nth derivative of f of t. Remember we said f of t is equals to y. So we can write it like this. Then which means the Laplace of the nth derivative of a function will be this one here. Then, you know this is a series, right? Then minus a series s raised to the power of n minus 1 minus v. Now, what is v and where is it coming from? Consider y raised to the power 0. If v is starting from 0, so when v is 0, you see that I'm left with s raised to the power n minus 1, which is this first term here. When v is 1, that will be n raised to, s raised to the power n minus 2, which is what I have here. So when v is 0, I will have no derivative of y, which is what I have here. When v is 1, I will have the first derivative, what I have here. So this is actually perfect for v. It might interest you that this particular series goes to n minus 1 because if we should have the first derivative, it should be no derivative. Second derivative, we have first derivative. Third derivative, we have the second derivative. So it goes to the nth derivative minus 1. So if this goes from 0, it goes to n minus 1. And that's it. That's how to prove it. Don't forget to like, share, and subscribe to this channel. And see you in the next video. Bye for now.